Yeah. Audio test. Yep. Okay. Audio test was successful. Let's see latency. Hold on. Oh, that's quite a bit. Last time we had horrible reactions using the ultra low latency mode that YouTube advertises that it has. So I'm using the low latency, which tries to keep it within 5 seconds. This is definitely, like, this is one of the few tutorials where I'm not expecting any participation whatsoever, so I'm not too worried about low latency. As always, stream begins in 9 minutes, so if you're watching this as a video afterwards, just skip ahead. Because I know a lot of people don't actually come to these tutorials. What we're learning is 100% and totally testable. Maybe not in this test, but on the final exam, I wouldn't be surprised if you saw a binary search tree. I genuinely wouldn't. I actually just realized I have people who... Okay, yeah, nope, that's a sex website. I have comments on my videos, but they are 100% and totally either bots or not real people. I don't need that. That kind of stuff's not really appreciated. Like, this is clearly branded as an educational video, and there are genuine, like, post nudes of yourself on Snapchat links being posted in the comment section. That's kind of scummy, like, not to be. Doot, 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 doot. Still no one showed up, but I've got 7 minutes. Current bit rate is higher than recommended. It's higher because I can support it and I want to avoid packet loss if possible. Like, I have the internet possible to stream 1080p if I so chose, but that A seems overkill for just a text editor, and B, like, the last time I tried that, it went horribly, and latency is bad enough. If I'm sending massive packets, I don't even know if this would literally do anything. So I'm going to avoid streaming packet sizes that require a 6,000 millibits per second or millibytes per second. Yes, I realize that my bitrate. They want me to use 2500 with a bitrate of... That makes little sense to me. Also, the audio bitrate shouldn't be 0. The audio bitrate should be 128. YouTube. Yeah, so there is audio being sent, so YouTube, bibbity boppity. Boop ba da doop ba da doop ba da doo doo doop ba doop ba ba doop ba ba doop ba ba doo doo doop ba da ba ba da ba ba da ba ba dee ba dee ba da ba ba dee doo doo ba ba doop dee dee baby doop ba dee da boo da da dee da da boo da dee. I'm just gonna turn my microphone down a smidge. Ba ba da da. 4 minutes. Still no one's coming. The announcement should have gone live, so you guys can see that there is a video. Then again, this is one of the most depressing times of the year, so I'm not surprised that no one wants to come on out. I will just teach to no one if I have to, but I am starting at 11:30. This is a topic that is long enough to the point where I don't really have the luxury of not starting at 11:30. Like there is literally courses in second year of comp sci that could spend 3 weeks on the topic that I have to now cover in an hour. But you guys are not scheduled to be here for another 3 minutes, and 3 minutes is a long time, so there's Jamrin. Hey, that money to make that mind gonna be the fine. Ah, hello, Sarah. All right, we're getting some people. Got 2 minutes. Still plenty of time. Still plenty of time. I got the stream chat back up and working. Not sure if I'm gonna keep it, but it's there. I told you once, told you twice, and so like a little ribbon neck by mine. Who's ready for binary search trees? Out of the 2 people who are present, one of which isn't even taking this course. This tutorial is very much not going to be interactive. I should say that right now. Like, this tutorial is straight up, I'm going to be coding something that's kind of time sensitive. Because binary search trees, they can take time. They very much can. We're not going to be doing it. Might come. Yay! I have missed my source of hugs in the world. Is this important to note for the exam? This is a recursive class, and I can almost guarantee, I cannot guarantee it, but I can almost guarantee that you will see something important. This may not be on test 3. In fact, I designed the object-oriented question for test 3, or I designed a object-oriented question. I hope it's the one that gets used, but yeah, this I would say is exam testable stuff, and this is going to be time consuming. That's one of the things that I don't like about binary search trees, but binary search trees don't have to be hard if you don't make them hard. So let's not make them hard. Okay? I believe that this is technically supposed to be tutorial 9, however, it's tutorial 10. So yeah, let's talk about what a binary search tree is. And I will say that binary search trees were the bonus on my exam in my year while taking this course. So yeah, let's get going. Hello, Haley. I just saw your message. I was looking at the rip from Sarah, and I was like, yeah, well, yeah. I have no notes pulled up. Nick gave us no notes. He just simply said implement a binary search tree. So that's what we're going to do. But first, I have to explain what the heck a binary search tree is. So, you on kazoo? No. So this is a binary search tree. What you were looking at right here is a binary search tree. A binary search tree is a recursively defined tree in which has a root node, sorry. So the number 7 here is the root of the tree. And then it has 2 subtrees, one to the left and one to the right. I'm just going to simply center myself a bit more on camera because I'm using my hands a bit. So the tree on the left, which is flipped, so I guess I should do this for left, considering that's what you guys see. The tree on the left contains only items smaller than the root. So if you notice, 7, 5 is smaller than 7, 3 is smaller than 7, 6 is smaller than 7, 1 is smaller than 7, and 4 is smaller than 7. On the right side, 12 is bigger than 7, 9 is bigger than 7, 15 is bigger than 7, 8 is bigger than 7, etc., etc. Also, we know that every item is a tree. So if we look at the same definition, 3 is smaller than 5, 1 is smaller than 5, and 4 is smaller than 5, but 6 is bigger than 5. 3, 1 is smaller than 3, and 4 is bigger than 3. Every item to the left is smaller, every item to the right is bigger. And that's all a binary search tree is. I want to make sure that I'm not losing you guys. So here I just wrote up a quick definition of how discrete mathematics defines a binary search tree. So a B tree, as it's commonly referred to, is either a leaf. If I pull the I left it up. So a binary search tree is either a leaf, as you can see on the diagram you're looking at right now. It is 1, 4, 8, 10, 13, or 17. I need the Chrome. I'm looking at the definition, but it's not the definition quite yet. So those are what are called leaves. If you look above them, 6 is also a leaf. What the heck is the point? The point is, you guys will need to know how to code this, and that's it. No. Binary search trees have one massive advantage. Let me ask you, in the tree you're looking at right now, how many steps does it take to find 9? Well, let's do it out. You look at 7. Is 7 9? No. Is 7 smaller than 9? Yes. Go right. Look at 12. Is 12 9? No. Is 12 bigger than 9? Well, yes. Go left. Look at 9. Is 9 9? Yes. You're done. Now let me ask you this. I'm going to hide the browser for a second. I'm going to pull up the VS Code, and I'm going to make an array. I got to make sure it's actually fair to say. If I wanted to do this, how many steps does it take to find 9? Well, let's take a proper look. Is 1 9? No. Is 3 9? No. Is 4 9? No. Is 5 9? No. Is 9 9? Yes. Done. For this, would you be given the set list of numbers? So you're not really given a set list of numbers, but you do know that all of the numbers are unique and follow the rules I mentioned earlier, where every number on the left is smaller, and every number on the right is bigger. So this data structure, the binary search tree, led to the creation of something called binary search, where in a sorted array, you could build the array into a binary search tree and then search the binary search tree. It is much, much faster. So we're going to talk about the binary search tree, and we're going to actually code up a binary search tree following this definition. This is the discrete math definition. You're either a leaf or you have a tree in the left and the tree in the right. It's really easy, but I have the rules here because these are the rules that we need to follow. Binary search tree is recursively defined. Every node has 3 parts: a root of the tree, which is the current value. So that diagram I showed earlier, 7 was the root of the tree. And then it had 2 subtrees, one to the left and one to the right. So let's go ahead and define just that first. So if we think about it, every tree has to first give a root. You can't just make a tree with no root. And what I'm going to do is say self.root equals root, and then I'm going to give it a self.left, and I'm going to set that to be none, because it's not implemented yet. We have no tree. Whoops. I accidentally opened a interactive code editor. Whoop. And then we're going to have a tree to the right. Oh my. I love VS Code, but I also hate VS Code. Like, I hate it with a burning passion. So this is going to be our tree. And the one thing that we need to do is, how do we get a tree to be more than a root node? Well, the first thing we're going to have to do is we're going to have to code some sort of insert method. Something where if I give you a tree, I want you to insert into the tree. And I want you to insert one of these binary trees. So you're going to have to create a binary tree and save it to self.left or self.right. So let's actually code insert. The first thing we need to do is it takes in a tree, and the tree has self.root. So first thing I want to do is I want to check, is the value we're inserting into the tree already in the tree? Remember, one of those rules I showed you, if I pull up that diagram again, hold up. This diagram contains no duplicates. A binary search tree can never have a duplicate number. If 7's already in the tree, then 7's in the tree. We know it's in the tree. So that's one of the really big important things we have to do. So if self.root is equal to whatever value I'm inserting, I just need to return. I need to break whatever I'm doing because I can't insert it. However, if that's not true, then I know that I have a root and I have a left and right in which aren't the current value. So now I need to determine the next step. Do I go left or do I go right? So if my root was 7 and I'm inserting 12, I need to go right because 12 is greater than 7. So what I'm going to do is if self.root is less than my value, this is my go left block. In the else case, this is my go right block. However, I'm not quite done because by default, self.left is none. However, what happens if I'm inserting into a tree where 7 is the root, 5 is left, and 12 is right? Now, if I say, okay, is 15 greater than 7? Yes, it is. I go right. However, 12 is already on the right. So I can't just shove 15 in and replace 12. Does anyone know what I'm trying to get at? I want to see if someone can type the word that defines what I'm saying. If you already have a tree in the right and you want to insert into that tree, what do you have to do? I'm kind of confused. Okay, I'll pull up the diagram again. I'll pull up the diagram because I think the diagram's easier to say. Loop-de-loop checks. No. So, if I have 7, 5, and 12, imagine the rest of the tree didn't exist. I only have this 7, 5, and 12, and I am inserting 15. I have to start at 7. I always start at 7. If 15 is greater than 7, I know I have to go right. Can I just put 15 here? Well, no. 12 is in its spot. So what do? I recurse. It's recursion. So if I already have a tree in my right spot, I then call insert on that tree. Does that make sense? Yeah! Ella got it. Ella got recursion. I want a recursive definition for inserting because, remember, every tree to the left and every tree to the right is a tree. I want to make sure that that's coming across. Like, you guys get that general concept. I see an eep. But new root does equal 12. That is a thing to say. So let's code the general concept. And I've been using go right, so I'm going to code the right one first. So if self.right is equal to none, this is my first case where I have no tree in the right-hand side. There is no tree. What I'm going to do is self.right is equal to a B tree of value. I'm going to create a new tree. I'm going to give the value is the root of that new tree, and I'm going to throw it in. However, if it isn't, what I know I have to do is I have to call, I think I have to say self.insert on self.right. Or actually, no. What it is it's self.right.insert value. Because self.right is the binary tree, and I want to insert this value. So this is self.right, this is value. And that's it. It's nice, it's quick, it's simple. What do I do for left? Well, nice and simple. I just take my definition that I just did, and change all the rights to lefts. Does that make sense? I want to make sure that you guys are keeping up because, like I said, this is 100% testable material. And it probably would be a bonus for you guys, but it is 100% testable. I don't think it'll be on test 3. I think it will be on the exam, though. So I need to make sure that you guys are keeping up. Okay, I've got one yeah. I want to be absolutely sure because if you guys want me to slow down or if you want me to redescribe something or anything, you let me know. I will do it. So that's insert. Let's see if it works. So why are you doing B tree value again? Okay, that I can answer. If we look at what describes a binary tree, every binary tree has either left or right being a binary tree. So if you look at it, the initializer takes in a root and returns a binary tree. So if I take a look at I'm going to keep pulling up this diagram. If you look at it, 7 is its own binary tree, but 5 is also a binary tree. 5 is a binary tree consisting of 6, which is a binary tree with no children, and 3, which is a binary tree. 3 is a binary tree with 1 with no children, and 4 with no children. This is why binary trees can be so confusing for some people. So I was going to say we should test it. However, I have a problem. How do I view the tree? This is one of the big things. I can't prove a binary tree is working unless I can see the tree. And at the end of the day, there is a quick way to do it. So what I could do is I could say tree equals btree 7, then tree dot insert, and I'm actually going to, that diagram I keep showing you guys, that's going to be the binary tree I make. That's going to be what I make. So I've pulled it up on my second monitor. Whoops. So, and it shouldn't matter how I insert these, because at the end of the day, as long as I insert them in the correct kind of order, they should work properly. Can you insert multiple at a time? I could code it that way, but that's not going to be how I choose to do it. You guys could 100% though take in a list of values and insert every value if you wanted. Nothing stops you. Keep cutting out. I have one person saying I'm still good, so I'm going to assume I'm good. I hope I'm good. So, this is a binary tree, and what I'm going to do is I'm going to pop open a terminal, and I'm going to say python -i / I'm in the wrong tutorials, binary search tree. Whoops. I forgot to actually give it the file. bst.py. So what I'm going to say is tree. If I look at tree.root, and if I look at tree.left.root, well, uh-oh. The left is bigger, and the right is smaller. So what did I do? What did I do? If the root is smaller than the value, whoops. If the root is bigger than the value, go left, because 7 is bigger than 5. Ha! I'm dumb. You guys are probably being like, man, you're a TA. You call yourself a comp sci? No. So if I look at tree, and I look at its root, 7. If I look at the left's root, 5. If I look at the left's dot right's root, well, that's 6. So I went left, and now I went right. I put you on 75% speed, and now you're better. Ha! Ladies and gentlemen, emergency announcement. Nick's wife is going into labor. Okay. Well. Oh my. Well, you're going to see a lot more of the TAs now. Yeah, so Swale will be handling the Monday announcements. I'm going to check the schedule Nick just posted. But, yeah, Nick has, yeah, Nick's wife's water just broke. Okay, anyways, this is annoying. Having to say tree.left.root, tree.left.right.root, tree. Nah. Hey, we're all excited, but we need to keep going. I've got a code. So I need to define a print. So what I'm going to do is I'm going to overwrite string so I can print the tree. I'm sorry, I know we all want to party right now, but I need to get the tutorial done. Oh no. Okay, oh, I'm flustered because I'm so happy for Nick. Okay. How do you print a binary tree? Well, what we want to do, one of the rules when it comes to printing a binary tree is you want to print everything in order. So I'm going to pull up the diagram. I know you guys love this diagram. Boop. And I'm going to explain what I mean by in order. In order is like following. You start at the very bottom left, and you print it. So you print 1. You then go up to its parent and print 3. You go then right and print 4. You then go up to its parent, and you go up to that parent, print 5. You then go down to its right, print 6. You then go up to that parent, and you go up and you print 7. And then you go down, 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 and you print 8, 9, 10, 12, 13, 15, 17. You print everything in numerical order. And this seems like a daunting task, but it is much, much easier than you think. For example, when I'm starting at 7, how do I make sure that 5 comes before 7, which comes after 12? Well, I'll just call print on the left tree first, then I'll print 7, then I'll call print on the right tree first, or the right tree after. Well, if I call print on 5, does the definition still hold? Well, I call print on the left tree, then print 5, then print on the right tree. So it still holds. So look at 3. If I call print on the left tree, then print, then... Oh, that still holds. Huh. So printing a binary tree is literally, and I kid you not, it is as simple as print the left tree, print the root, print the right tree. So that's pretty cool. Let's go ahead and code it. Kill the browser. So, if self.left equals none, what does this mean? Well, there is no left tree. So what I'm going to do is I'm going to return an empty string. Else, I'm going to return the string of self.left. But I don't actually... So this isn't quite complete, but this is basically like... So then I'd be like... I have to make it an actual string. So answer equals an empty string. And then what I would do is answer... We're using... So underscore underscore means it's built into Python. So the 2 underscores means that string is built in, and I'm doing this specifically so if I say print tree, I want this to work. Is that using recursion on it again? Yeah, we're gonna be using recursion, but I'm only using underscore underscore, so that way I can just call print. I'm lazy. So ans plus equals nothing. Else, what I want to say is ans plus equals string left. I mean the second part, like within string. It's the same recursion. I want recursion. So if I want to generate the string of the left, I could call print left if I wanted. But I just noticed if I'm adding nothing to the string, then there is no point to me even having that block. So what I'm going to do is I'm going to say if self.left is not equal to none, do that. Then what we're going to say is ans plus equals self.root. Now remember, self.root is an integer. It's not a binary string. So if and I need to make sure though that I'm calling the string. Also, now that you mention it, I don't need the double underscores here because string is a built-in function in Python. So this and this are equivalent. If I wanted to use the double underscores, it would be that. Good. Thank you, Ella, for pointing that out, because I very much missed that. So, yes, you call string like this, or you call string like this. I completely and totally forgot. And then, of course, we do the same thing for write. And finally, what do? Well, we return the answer. Yeah, Ella definitely called me out on that because she is correct. You don't need the double underscores for string inside, but you do need it if you were to call it as that type notation. So I think that this actually does what we want. It might not be pretty. One thing I'm going to do is just that to make sure that there is spacing. So if I run this, it should print our binary tree in order from left to right. And 1 3 1 5 1 7. Did I forget to change a left to a right? Did someone not let How many people were screaming at me? How many people were like, Mark, we are disappointed in you. You have failed us as a TA. Because if you weren't, then that's fine. Run the code, come on. I want to see it work. 1 3 4 5 6 7 8 9 10 12 13 15 17. Woo! It worked. It prints in order. I didn't mean well, I saw that and was skeptical. Yeah, no. I deserve to be put on trial. So, there it is. It prints in order. That's exactly what we wanted. It's beautiful. However, we're not done. There is one more big component of a binary search tree. Can anyone tell me what I am missing in this binary search tree? Is anyone able to see what I am missing in the binary search tree? If you haven't figured it out, I am emphasizing the word. I know that there is delay. I know it is a bad delay, but search! I'm missing search! How can I be done if I have not missed? There is no search in my binary search tree. I'm a fool. So, how do I search? How do I do it? If I take in a self and I want to return true or false, what do I do? Ladies and gentlemen, I pull up the diagram again. Binary search tree. I start at the root. What? Everyone, give me a number. The number in the tree or out of the tree. I want to show you how search would work. First number I see is the first number I pick. Preferably don't give me 7. Please, for the love of God, don't give me 7. The first thing we're going to say. 10! I can do 10. I can do 10. I can do 5. We'll do both. I love you guys that much. So, I want to search for 10. And I have to start at 7. I have no choice but to start at 7. Let me ask you this. Is 10 smaller than 7? 420. I'm not doing 420. Blaze it. Is 10 smaller than 7? I'm really hoping that you guys can answer this, but I also know that you guys are probably a little further behind. No, 10 is not smaller than 7. I would be a fool for thinking so. So, which way do I go? Left or right? If I'm on 7 and I'm looking for 10, do I go left or do I go right? I believe in you guys. I believe that you guys will catch up eventually. I'm going to actually quickly take a sip of my Conch Zero. Did I see a... I see a right! Woo! Righto indeed. So, I've gone right. 12. Is 12 10? No, 12 is not 10. Do I go left or do I go right? I'm gonna skip the delay. I go left. So, I'm on 9. Is 9 10? No, I go left or right. Woo! I'm gonna go right. I go right to 10. Is 10 10? Yes! I can return true! I'm sad to say, what if it's not in the tree? 420. Is 420 bigger than 7? Yes. Is it bigger than 12? Yes. Is it bigger than 17? Yes. Is it bigger... Or, sorry, is it bigger than 15? Yes. Is it bigger than 17? Yeah. Uh-oh. Oh, no, 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 no. I can't go right. I can't go right. There's no right. I know it should be on the right, but I can't go right. What do I do? There's nothing down here. Do I cry? Do I have a mini mental breakdown? What do I do? Terminate! Exactly! It's not there! No matter how hard I try, I'm not gonna find it. There is no 420 in my tree. We insert and then search. No, 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 no. So, you can add it. You can 100% add 420. However, that's not the point of the binary search tree. The binary search tree, if you're looking for a number and the number doesn't exist, you don't just add it. The number doesn't exist. You're not going to mutate the data you're working with. So let's code it. Step 1. I've got a lot of energy right now. Step 1. If self.root, and I just realized I need to pass in a value. If self.root equals value, what do? I return true. No, duh, I return true. I found my value. However, if I didn't, if self.left equals none, well, that's not right. I don't want to automatically go left. I'm going to just steal my code from insert. Because it worked, if self.root is greater than value, then go left. And if self.root is less than value, go right. It's just these that need to change. So, all of these become returns. So, if I have gone left, and if my left tree is none, what do? Well, you guys already said it. I return false. I can't go left. There's nothing left for me there. That was a good pun. If any of you boo me for that, I'm going to come find you and tell you you're wrong. Don't boo me for my amazing humor. However, if there is a left tree, well, self.left.search value. Same thing here, except with right. Nice, quick, simple, right. And that's it. So I should now be able to tree.search. The 3 numbers you guys gave me were 10, 5, and 420. So I'm going to search for 10, 5, and 420. So 10, 5, 420. And if I run this, I should get true, true, false. Simple as that. True, true, false. Woo! And that's a binary search tree. And we have 15 minutes left. So, Who wants to spice it up a little? Who wants to get a little crazy? I want to see how many people are genuinely like, yeah, I want to spice it up. Okay, I'm seeing one person going, okay. Let's do it. Okay, I'm seeing a lot of let's do it. Let's go back to a binary search tree. This is already crazy enough. I do like sriracha. Okay, no. I'm sorry, Sarah, you've been outweighed. What happens if I want a binary search tree, but I don't want less than and greater than? Ooh. A binary search tree holds a principle. The thing on the left is when a function returns true, and the thing on the right is when the same binary function returns false. Oh. So what if I could customize the function that decides if you go left or right? Okay. No, let's do it. So we're going to add in a predicate. And self.predicate equals just that. A predicate is a function that returns true or false. And what I want to do is I want to modify insert and search to use this predicate. This is going to be fun because the code doesn't really change. Here is the if statement. If self.root is greater than value, well, if I call self.predicate on self.root and value, there's your go left right there. And the else statement goes right. Does that make sense? Same thing for search. If I want to use this self.predicate, I could change that to be that. So now my binary tree, if I wanted the exact same binary tree, lambda x, lambda xy returns x greater than y. So your booleans, instead of greater or equal to, it tells it which way to go. Exactly. This function. So a binary tree is just like this. So if I print this, I should get the exact same tree. Nothing should change. And yet it did. Why did it? Can anyone see why self.predicate did that? Why again would this be better than what we had before? So if I got this working, let me ask you this. In a family, say you've coded a class of a family, a class of human beings. Can you say human less than human B? Like, could I legitimately say human A less than human B? Is that technically valid? Well, no. What quantifies a human? So in a class, what I could do, however, is write up a function that takes in human A and human B. Also, perhaps not working because we're not giving it anyway until what self.predicate is, or is that a lambda function? I've passed in a lambda function. Lambda xy returns x greater than y. Let's just see if it's because I did something stupid. Let's just pass in f. So just if I have some function human A and function human B, what if I want to say return human A dot height greater than human B dot height? So my binary tree would not have to change if I could define a function. So every root would just be a human class, and the function would get the required information to go left or right. That's why this is really cool and really valuable. The binary tree would never have to change. You would just have to code a working function. Self.init missing predicate. Ah! I didn't actually pass in my self.predicate. Oh, you guys probably were like, Mark, you fool. I have to give the function to the children. I can't create a tree, give the function only to the root. Sorry, I was a fool. But now I can sort on any function. So if I wanted to reverse the binary tree, I could simply do this. Boom! The binary tree is now reverse sort order. What if I wanted to say x mod y was equal to 0? I don't know what this will do. I genuinely don't. Well, that's funky. So the thing is, you have no idea like how much something can change when it comes to code like this. So one thing I'm going to do is I'm going to modify my print, because I genuinely, if I showed you this, can you identify what the root node is? No. So what I'm going to do is I'm going to change the print to basically put a new line character. Ooh, how do I want to do this? Basically, what I want to do is I want the roots to be on a different level than its children, but I don't know. You know what I could do? I could get it started by doing this. And here. What I'm going to do is I'm going to put left arrows and right arrows. And I'm going to see. So if you look, 7 is the parent of 1 and 5, which is apparently the parent of 3, which is a parent of 6, which is the parent of 4. Then so it looks like 12 is the root node here. This is actually interesting. It's not the cleanest print. I might have actually a binary tree printing function from one of my classes. Just let me see if I can find it real quick. Because 2xb3 had us working with binary trees in lab 6, I think? No, that's red-black trees. We would have done binary trees before red-black, so lab 5. He would always give us functions designed to print the tree. That's a heap. A heap printing should be roughly similar, because a heap is similar to a binary tree, but with a different rule. So what I'm going to do is I'm going to steal the string function, and I'm going to see if I can modify the string function. But I just want to say, the tutorial is over now. If you guys have questions or requests or anything, this is the time to do it. But I'm going to see if I can get... Thank you, Mark. Yeah. No, this is designed to work with his list. That's unfortunate. If you guys have questions, go ahead and ask. I really wanted to get this printing in a fancier way, but... oh well. Given the opportunity, I would just hang here all day. Honestly, tutorials, if you get a good tutorial runner, they can be fun, but not every day you're going to get a tutorial runner that is cool. I really want to get this printing. Luckily, I have my office hours in 3 minutes, but I really want to... So... So if there is a next line, or if there isn't a next... let's do it this way. Let's see what that does. So it looks like 7 is the root node and goes left to 1 and right to 5. Then 1 goes right to 12, because remember, we print the left subtree first, then the right subtree. Then there's a 3 roots. So there appears to be 2 roots. Again, I can't quite see... one thing I could do is I could open this as a Python interactive terminal and see what tree.root is. Tree.root is 7. And it has no left. Oh, whoops. Now I've got myself genuinely fascinated. So it goes left and then doesn't go right again. Does it go left again, though? No. So it goes left only once and then everything else is on the right subtree. That's pretty cool. And that's all things I would have never noticed if I didn't bother to look. Anyways. Yeah. My tutorial's over. I am heading to my office hours now. You guys are welcome to meet me there if you so choose. Either way, I hope you guys enjoyed this one. But yeah, bye-bye now.